Welcome to our lab on vibrations. We're going to look at vibrations in two different mediums, vibrations in a string and vibrations in the air. Before we get started, let's take a look at some formulas that are given to us at the beginning of the lab. Now I have on this whiteboard here the two formulas that are given. This says that frequency times wavelength, which were defined for you in lecture, is equal to the square root of tension divided by linear density, mu. And so the tension, this equation is for waves in a string. So the frequency of the wave times the wavelength is equal to the square root of the tension, that means how tight the string is, the tension, divided by the linear density. Linear density relates to volumic density, rho, in this way. Volumic density is mass divided by volume. Linear density is mass divided by length. Here's another equation. This looks probably more familiar. It says that frequency times wavelength is equal to velocity. So when you look at these equations, they don't automatically look as if they're linear equations, but they are, and here's how to show that. Divide both equations by wavelength. And here's what you get. You get on this side, you get frequency is equal to the square root of tension divided by linear density times 1 over the wavelength. In this equation, you get the frequency is equal to velocity times 1 over the wavelength. And now you see these are linear equations. You've got a variable here times is equal to a constant times another variable, 1 over wavelength. And these are linear equations in the form y is equal to m times x. So therefore, if you wanted to verify these relationships, you would plot frequency versus 1 over wavelength, y versus x, and then in the slope of this graph, the slope would be equal to the square root of tension over linear density. The slope of this graph is simply equal to the velocity of the wave. So, in looking at that first relationship, we have a string. And this string has an unknown linear density. So that's something that we're going to be able to maybe solve for. Now, I have this string going over this speaker. There's a speaker in a glass encasement here. And this speaker is going to vibrate when a signal is sent to it. That signal is coming from this function generator. Now the function generator should be turned on. We're going to have its volume all the way up. The gray buttons here on the right side of it should be set to sine wave. And the selection for frequency should be set on 50. We're going to vary around 50 hertz. I don't think we should go up as far as 100. We'll be able to audibly hear the tone and the room will get noisy. So now, anytime you've got a string, you want to create a wave on it. I'm going to send it through here. You can see that it's shaking. I want to put some tension on it. And my tension is around 100 grams. And to keep that tension on the string, I'm going to drape that over a pulley. So I'm shaking one end of the string. The other end here is fixed at the pulley. And as you can see, I'm starting to get some waveforms. If I vary the frequency, I can get a standing wave. Look at this, has 1, 2, 3, 4 loops. As it turns out, each loop is half of a wave. So here's 1 wave, 2 waves on the string. If I wanted to know the tension, well, that's easy. It's just mass times gravity. My mass is 100 grams. If I want to know the frequency, that's right here. This says 53. My frequency is 53 hertz. And then if I need to know the wavelength, that's pretty simple too. I know there are 2 waves here. So if I knew the distance between here and the pulley, I would know the wavelength. So I take a meter stick and I measure this distance, divide it by 2 because I have 2 waves, and that gives me the wavelength. So now I know the wavelength, I know the tension in the string, and I know the frequency. And all I have left that I don't know is the linear density of the string. Well, here's how we'll do that. We're going to make a plot of frequency versus inverse wavelength. And so I might change the frequency. Here I'm going to change it up a little bit. And now I've got a situation where I have 3 loops. You might see those. This is 1.5 waves, so I divide that length by 1.5 to get the wavelength here. I have a new wavelength. It's a little longer. I have a new frequency. It's a little lower. But by plotting multiple values of wavelength and inverse frequency, and then taking a look at the slope of the graph, from the slope of that graph, I can set the slope equal to the square root of tension over linear density. Okay? And if I know the tension, that's something I can put in. I can solve, using the slope of the graph, the linear density of the string. Just to check myself, here in this pad balance is 10 meters of string. Now, if I know I can divide the mass into the length to get the linear density, so I just mass this, divide it by 10 meters, and I get the linear density of this string, which incidentally is the same type of string that I have here. So therefore, I have something to compare to now. So I found the linear density using the slope of my graph, and I found it more directly here. I can compare the two using percent difference. Now my other equation was, I looked at the relationship of frequency, inverse wavelength, and velocity. And so to take a look at that, let's examine this tube. Now this tube, you can see has markings on it. There's a little meter stick tape on this tube. Well, what's really neat is that I have these tuning forks, and the tuning fork says B480. The 480 means that produces a frequency of sound that's 480 hertz. Now I'm going to ask you not to hit these on the tabletop. That's bad. Hit them instead on this rubber mallet to produce a tone. Now I'm going to put that tone into the tube. And when I move this plunger out, listen, I get a loud tone there. This tells me that there is a node here. If I can find 2 nodes, that 2 nodes separate a half wavelength. Okay, so let me find the other node. This node was around 17.5 centimeters. Listening. I found another node. I'm moving the plunger out until it reached here. Now the plunger is at around 52.5 centimeters. So the difference between 17.5 centimeters and 52.5 centimeters is equal to half of a wavelength. So if I know the length of half a wave, I just double that to get the length of a full wave. And so now here I am gathering data. I have my frequency and I have my wavelength. Now I have several different tuning forks, so therefore that's going to give me several different values of frequency, several different values of wavelength. And now if I plot frequency versus inverse wavelength for all my data points, I'm going to get a graph, and the slope of that graph is going to be the velocity of the wave. As it turns out, that velocity is constant because it's just the speed of sound in air. And in your lab, you're given a value for the speed of sound in air, or whether you can calculate it depending on the temperature and the humidity, or maybe just the temperature. And then compare the slope of your graph of frequency versus inverse wavelength to the given value for the speed of sound in air using percent difference. So that's 2 methods that we use to verify these equations for frequency and wavelength. So we're looking at the relationship between frequency and wavelength using two different experimental methods.